This is lecture number 26 of the course ME314 Fluid Mechanics 2, and this is the second lecture of this week. We have, in the last lecture, we talked about different types of turbines and their classifications and the concept of degree of reaction. Today we will look into this efficiencies of in general first with the pumps and turbines by comparing the formulas, and Euler equations are exactly the same. Only thing is just the objective is different. Then we will go into this general energy equation, which is equation about all the available heads and the head related with pumps and turbines and the head losses. In this we will solve the problem related with turbine, and we will go through that the energy equations and formulas for efficiency and Euler equations of turbomachines and how to address them and how to solve the velocity triangles. All that would be included in this particular problem. Then we will go into the laws, affinity laws for turbine. We have already seen those similarity laws that is being used in the pumps, and the similar format that will be used in the turbines, but in turbines and pump the output and input is different. And then we will go into the concept of turbine specific speed exactly in the same manner as the specific speed for pumps, which help us to classify different types of turbines. So let's look at this energy balance for the pump. So the pumps are the devices which actually transfer the energy from the fluid to the shaft. So whatever the energy that is being supplied through shaft would be available energy that is actually the input to the pump. So that is something. Shaft power is an input power, which is T times omega, and some part of that available energy which is being given to the shaft is supplying through the shaft to some part is taken by the fluid, and that what we call it a useful fluid power, which is rho g qh, and hp is the pump head, actually the head developed by the pump. And not all energy is converted into useful fluid power. Some of the power is lost, we call it in hydraulic losses. Some of the power we have addressed is due to the leakage called volumetric losses, and some of due to this mechanical element, and each mechanical element has certain friction. So these losses are exactly the same. That is what we have learned in pumps. So our efficiency for the pump would be always the efficiency is something which is the desired output, and for that desired output, what is the required input. So whenever you write down the formula for anything, any device, you always look at not as an output over input, but always look for the desired output. So in desired output, your fluid, you are supplying power from your motor to the shaft, and then you need to supply that power to the fluid so that the head of the fluid is raised. So that is what your desired objective, and that is actually the power for the fluid, but here it is output is in the numerator. And for that desired output, supplying power to the fluid, you need to supply power to the shaft. So that would be your input power. So for your formula for your pump efficiency would be this. The same idea works for the turbine also. In turbines, the available energy is in the form of the fluid. So that is the head available to the turbine, and that same energy is transferred to the shaft, which would be your mechanical power, and that is T omega, which is actually, in case of your turbine, that is an output, and in case of turbine, this fluid power is actually your input. and the rest would be the same as in the hydraulic, volumetric and mechanical losses in the turbine too. So the turbine efficiency would be the desired output here in turbine case would be the shaft power. More the shaft power, better would be your turbine. And for that shaft power output, what you need is a fluid power input. So your fluid power input would be that component, and your shaft power is that component. So just topple the formula, because in pumps and turbine the only difference is the output. Here fluid power is an output, here shaft power is an output. The rest of the things are exactly the same. In typical scenarios, we have seen in the pump, what you need is you have some device, and you have something at the inlet of the suction side of the device, and something is you need to raise the head, and something is delivered at an outlet. So what you need is you need to apply the energy equation between section 1 and section 2. The similar type of thing to be done in case of turbine. So you stored energy through some height, and through some penstock or whatever you call it, some sections you need to provide water with certain flow rate, and you the head, which is that is actually the tail race part. So this head is actually, that is the head available for the turbine to work. And so this is the typical arrangement between section 1 and section 2. So here you have a pump, here you have a turbine. So your energy equation is exactly the same for both cases. What you call it, this is something which is available energy at the inlet, and so at section 1 or that section, whatever the energy available in the form of the pressure head, velocity head and kinetic head. This is kinetic head, what you call it, a velocity head, and this is an elevation head. So energy in the form of pressure, kinetic and elevation head. Some energy is given to the pump by means of some external means, so that is available at the section 1, so that pump can run. So some energy will be at the outlet in the form of the pressure head, velocity head and elevation head. And if you are using some devices like turbine, so there would be some head associated with the turbine. And for example, in this particular case there is no turbine, then the turbine head would be 0. Or in case of the turbine, this pump head would be 0. And obviously whatever energy is going in is an out. So you get something out, but you have certain losses, what you call it, your hydraulic losses. And this head losses would be, we already have seen that formula for in piping system. There is some pressure head loss due to the friction, and due to the small dia of the pipe, and due to the flow rate requirement. And similarly, there is some minor loss factors, K factors. So there are components involved like joints, like valves and all these things. There is some head loss available. So this is a simple energy equations, and I hope that you have seen it in your FM1 course as well. So this is actually the same thing. So this is a Bernoulli part, which is without a loss part. So you have some energy available in the form of the pressure head, velocity and elevation head at section 1. So this is a pump head, and that is something in an outlet. The pressure, velocity and elevation head at the section 2. So that would be the section 2, and the turbine head, and then the sum of the head losses actually. So this equation is very useful in solving problem related with turbine, which most of you have done in your FM1 course as well. Okay, now let's see, we have a problem of turbine, and this is a typical setup in the turbine. You have a water reservoir, and you have a dam, and water taken from this penstock. and then it goes to the generator, which is your turbine actually, and the shaft, electrical component of that shaft is connected to the generator, and this is a draft tube, and we have already seen this level of water is called head race and upstream side, and this is at the downstream side, it is actually called as a tail race. So this is a typical arrangement that is for the hydraulic turbines. So the question here is you have an inward flow reaction turbine, which is a vertical shaft turbine. The sum of the pressure and kinetic head at the entrance to the spiral casing is 132 meter. And vertical distance between the this section and the tail race from this section is 1, which is actually your pressure and kinetic head is altogether is given as 132 meter here, and from this section to tail race the vertical distance is 3.3 meter. The peripheral velocity would be your tangential velocity, which is your blade velocity, that is actually given is 33 meters per second, and you know at the runner inlet and outlet your peripheral velocity remains the same because that is your blade velocity. What is given more is the radial component of the velocity of the water is constant. So, and discharge from the runner is without weld. So what does it say is that the radial component of velocity is constant. So it means VR1 and VR2 is same value at 11 meter per second. And another information is that the discharge from the runner, so discharge from the runner is without weld. It means at the outlet of the runner V theta 2 is 0 because there is no weld component. So tangential component is 0. So there is only a radial component at the discharge of the runner. What next is given is you have hydraulic losses associated. So there is a loss between turbine entrance and discharge from the guide vanes. So because when fluid enters, first it goes to the guide vane and then it goes to the inlet of the runner and then it is the outlet of the runner. So at the turbine entrance and discharge from the guide vane. So it means when discharge from the guide vanes, it means it is entering to the runner. So your losses are already of head loss of 4.95 meter. And in the runner there is loss takes place of the head or 8.8 meter losses in the runner, and some losses in this draft tube which is 0.88 meter, which is much smaller, and some of the energy is rejected to the tail race because your velocity at the downstream side may be some velocity so that the water should not accumulate here, water must leave, so some of the energy has to be dissipated to the tail race as well. So the head associated with that energy would be 0.55 meter head, that is actually energy by which the water would be flowing in the downstream side, otherwise all the water would be accumulated here. So this is what the problem which is given here, and okay, what to work out? Work out is you need to work out the guide vane angle and the runner blade angle at the inlet. So blade angle is beta 1 and your guide vane angle would be alpha 1. So that is the angle by which the fluid tries to enter to the blade. So that would be your alpha 1. And the next part of that working out, what we have to work out is you need to work out the pressure head at the entry and the discharge from the runner. So at the runner inlet and runner outlet, whatever what are the pressure heads at runner inlet and outlet. Entry is an inlet and outlet is a discharge. So that is something we have to work out. So before solving the problem, any problem, engineering approach is important. Engineering approaches, the problem can be half solved if you understand the problem. Most of the students have the difficulty in they don't spend much time on understanding the problem. So once you understand the problem, then the solution is much easy, and we will see in this particular example that's how things works. So let's say the first thing is you have to draw the schematic or whatever the problem is, and then the next step is whatever given is the peripheral speed is given, r omega is given, which is 33 meter per second, and we already have seen that the fluid enters and leaves in the radial direction. So that VR1 and VR2 would be 11 meter per second, and V theta 2 is 0 because there is no will at the discharge that is mentioned in the problem. So that is something given from the problem. As you know, this formula for the head that is actually available when your pre-will component is 0. So you know the formula for your pump Euler equation of turbomachine head is 1 upon g times u2 peripheral velocity at the outlet and tangential velocity at the outlet. Since v theta 2 is 0, so this component is 0, so head would be that case. So since I am writing for pump, so it is negative, but for turbine it would be opposite in sign, that would be positive. So the magnitude of that head would be associated, because v theta 2 is 0, so it is only u1 v theta 1 over g. So that is something our runner is going to utilize that head. So it means this head is something where we are going to subtract all the losses. So what we do is, next part is this head utilized by the runner is what is the total head available. So that is actually 132 meter plus this 3.3 meter, the difference between the head race and the tail race. That is actually the two water levels that is available, but the useful head would be after subtracting it from all the losses. So I have all the losses. I have 4.95 meter, that is in the vanes and the guide vanes, and this is in the runner, and this is in the draft tube, and this is the kinetic energy head rejected to the tail race. So all the losses have been summed up. That would be your hydraulic losses. So in this case you will evaluate, that is actually head available for turbine is only 120.12 meter. So out of that 132 plus 3.3, 135.3, only available head is 120.12, which can be converted into useful work. So that is head. As you know from this formula, we can easily work out the tangential component of the velocity v theta 1, because u1 is already known, h is you know by available head, and the hydraulic losses subtracting it, you know the knowledge of h, g is 9.81. So your velocity, tangential velocity at the inlet is this magnitude is 35.71 meters per second. So here we know the next thing is to work out the velocity triangles, because at inlet you have, at outlet we have already seen the tangential component is 0, so only component is, that is actually the radial component, and this u2 and u1 is, we know that 33 meters per second, so this length is 30. So we already know this v theta 1 is a bigger number, that come out to be 35.71 meters per second. So that is something, some bigger value, 35.71 meters per second. So this is actually the relative speed, which is actually your blade angle at the inlet of the runner. So this is your runner at section 1, and this is the discharge of the runner, that is at section 2. So you need to properly draw your velocity triangle for that particular type of turbine, which is a vertical axis turbine. Here the fluid tries to enter through a guide vane, so that would be your guide vane angle. So that would be your absolute velocity of the fluid, which makes with the tangent, that would be your angle alpha. So this one would be your angle alpha, and beta 1 would be your blade angle. So from this geometry you can see that if you know VR1 is already known, which is 11 meters per second. So this this length is 11 meters per second, this is 33 meters per second, and this is 35.71 meters per second. So it's not on that scale, but you should make it, draw it, better try to make it on a scale. I mean, so that you have some feeling of that, because I have copied the velocity triangle from some books. So typically here alpha 1 comes out to be 17.12, that's a small angle. So here it is a bigger exaggerated view is shown, so that comes out to be that guide vane angle, which is the one of the unknown, that is something to have to work out. And this formula is tangent of alpha means the perpendicular over base. Perpendicular is VR1, which is 11 meters per second, and the base is v theta 1, which is 35.71 meters per second. So you know this angle alpha 1, which is your first unknown, and then you can easily work out this beta 1. Beta 1 would be perpendicular over base. So perpendicular is VR1 and the base is this distance. So you know V theta 1, you know U1. So 35.71 minus 33, that would be the difference, this difference. So in this way you will be able to calculate this runner braid angle at the inlet. So the first part of that has been done, and now we are in a position to work out the magnitude of V1, because we know everything. We know the VR1, we know this alpha 1, so we can easily work out sine of alpha 1 would be perpendicular over hypotenuse. So perpendicular is known, hypotenuse is an unknown, so that is something we have worked out. So that V1 is come out to be much bigger, that is 37.37 meters per second. Okay, then you see then first, that is the first part we have done, and the second part is you have to find out the pressure head at the entry of the runner. So that is our typical schematic, and we need to apply your energy equation between tail race and this section 1. So once we see that we have the energy equation available like this, so the same energy equation apply between this section and this section. So at that section what is available is this 132 plus 3.32 is available at that section at the tail race, plus there is at that section there is no pump work, and at section 1 you have certain pressure head at the entry, and that is a kinetic head, and there is an elevation head at 1, and this between this and this at that section obviously the turbine work is 0, and this would be your head loss that is actually taking place at that section. So you have used that energy equation here. So at that section 1 you have that pressure head, kinetic head, elevation head, and so V1 is already known, we have worked out. Z1 is would be in that case would be 3.3 meter. So we just substitute the value of Z1 and V1 here. So the only unknown in this equation is P1 upon rho g. So that is something, after substituting all the values, I got the magnitude of the term P1 over rho g. That would be the pressure head only that is available at the section 1, which is actually your runner inlet. So that is the first part, and the next is the pressure head at the discharge side. Discharge side is the runner at the runner outlet actually. So what I am doing is I am applying the same energy equation between turbine entrance and the runner outlet. So if you see your turbine entrance, so it means the available energy is in the form of the pressure and kinetic head, since at 1 there is no pump involved, but here because we are between section 1, between the turbine entrance, before the section 1 actually, you have the turbine installed. So there is some pressure at the section 2. Section 2 would be actually the runner outlet. So there is a pressure head at the discharge side, velocity head and elevation head at the discharge side Z2, and there is a turbine power, which is a turbine head, that is 120.12, and obviously there is a losses takes place from the section at which guide vanes and the turbine inlet. So this is that, and 8.8 meter is the at the turbine outlet. So we are only at that section, we are not going into the draft tube. So the head losses in that case would be 4.95 meter from the guide vane to the runner inlet, and at runner, within the runner, the head losses are 8.8 meters. So apply the energy equation. So only unknown here is because V2 is we know that V2 is same as VR2, which is 11 meter per second, and Z1 is same as Z2 because at inlet 1 and at outlet 2 is actually, I call it a runner outlet, because the both runner inlet and outlet, the elevation is same 3.3 meter. So I substituted Z2, I substituted V2. The only unknown in this equation would be our pressure head. So here we have seen that the pressure head at the outlet come out to be minus 8.04 meter. So, and at inlet we have seen that it is something a bigger number, 55.87 meter. So it means this difference is actually the pressure drop that takes place in the runner, and that is actually a feature of the reaction turbine, because pressure head, not just some of the pressure energy, available energy is converted into kinetic head in the guide vanes, and then the energy transfer takes place in due to the pressure drop in the runner. So because that's a negative pressure, that's a higher pressure, this forces the this higher and lower pressure difference forces the fluid to move into the runner, so that the energy interaction takes place. So this problem covers energy equation, covers velocity triangle, and covers everything that so far we have learned. So you see, the problem is easy once you understand the problem. Okay, that is actually the key. Okay, now go into the laws, affinity laws or similarity laws for turbine. It is exactly the same as we have done for pumps. So here, first of all, the impeller dia of the geometry is fixed for an impeller, and Q is the flow rate. So flow rate would be directly proportional to the speed of the shaft to which we are getting an output power, and H is our net head that is available for turbine to transform into useful work. So that is, your turbine head would be directly proportional to the square of the speed, and the power is the cube of that speed. We have already seen once your dia is fixed. Or the second law is, when your shaft speed is fixed, then your flow rate would be proportional to the size. It is cube of the diameter of an impeller. So head of an square of the head of an impeller, and power. So if you want to calculate power, either you know the geometry, then you need the speed of speed can be worked out if you know the angular speed, or if you know the RPM available, then you can work out the power associated. Similarly, if your speed is fixed, it's not changing, because you cannot, that is usually happen in pumps where you don't change the motor for the running the pump. So but in turbines actually you change the flow rate, you change the head, and you get different power, because in different seasons your dam is having different heads. So if you have different heads, then obviously at different heads with the same geometry and same you can run at different speeds, you could get different powers. So the laws according to that is exactly the same relation. We have seen it's the same thing for the turbines, as the same thing for the pump, the same laws for the turbine, because you know power is rho g h q. So this is rho, and g is a constant, because g at 1 and 2 are same, so don't need to write down. So and h is n and d, n and d is h, and q is n and d, so q is here, so everything is here. So these are the basics, and power can be derived using this. So not so difficult to derive. I have just put the result. These results helps you if your different diameters, or if your different head, what would be your different powers. So such problems you can solve using these affinity laws or similarity laws. Their performance is exactly the same we have done for pump. You have some flow coefficient, which is CQ, which is the flow rate requirement and the speed and the dia of the impeller, and then the head coefficient, which is head available, and the speed and the dia, and then power would be rho times n cube times T5. So kindly correct it properly. In pump slides I have used n square, but actually it is n cube. So correct those in your pump slides as well. And so you can easily work out the formula for the turbine efficiency of the turbine, which is opposite in that case, because in turbine the desired output is the shaft power, and for that desired output you need to give power to the fluid. So your fluid and head coefficients would be in the denominator. For pump the formula would be opposite. So power transfer to the fluid divided by what is input for that desired is your shaft power is in the denominator. So that would be swiping it from numerator and denominator, then you would have the same expression for pumps. So as you know, the performance curves for turbines like the same as this is for Francis turbine, and you see your fluid coefficient is on the left hand side and your turbine efficiency on this right hand side. So as it is multiplier by 100 of this coefficient. So as you increased your flow coefficient, you increase your power you are going to get, and lower power once your efficiency is low, and higher power and efficiency is also higher, but this higher require some higher flow rate as well. So your flow rate requirement would be higher. So these are typical performance curves, and this is something for this is Francis turbine, which is a mixed flow turbine. This is a Pelton wheel, which is a tangential flow turbine. So in that case, it's almost a straight line like behavior for Pelton wheel, but for Francis it is like relatively efficiency is varying from 0.84 to 0.9. Here it is almost 0.8, 0.9 for most of the operating conditions. So that is actually the performance curves gives you the difference by which how the devices are going to work. And we can see that the idea for calculating the classification is based on the idea of turbine specific speed. Similarly, we have a specific speed for pumps. So if your power coefficient is having a power of 1/2 and a head coefficient with a power of 5/4, then you end up with the formula in which P is the power output of the turbine, and head is the turbine head available, and N is the speed. So that would be your turbine specific speed. So with that dimensionless quantities, we can classify different types of turbine based on one single parameter. We have given a name called specific speed of turbine. So as you see, impulse turbines, their efficiencies are almost 0.87 to 0.9, not much change. But Francis and Kaplan has some, for example, Kaplan turbine would have higher turbine specific speed, and Francis would be in the middle. So that is a tangential flow. That is axial flow. Kaplan is an axial flow where fluid is going parallel to the axis of rotation, and this is a mixed flow. Francis is a mixed flow turbine. So based on the turbine specific speed, that turbine specific is a single parameter which takes care of the different heads, different power and different speed put together into one number, and that one number signifies that this is a particular class, and the efficiency is based on that this number, and this is very useful in classifying different types of turbines. So the problems related with the turbines and pumps are exactly the same manner. I have already used such formula for homologous pumps to use the concept of specific speed. So I don't need to use the same thing for turbine, as already have done it in the pump cases, and I've used the problem for the similarity rule as well. So I'm not doing it in turbine because it is exactly the same. So this is how we have finished the whole topic of turbo machine. So I finished my lecture today as well today because we don't have any more slide. Let's just stop.